So, first of all, a lot of what I want to talk about is related to my earlier investigations that have to do with, how do we discover good representations that disentangle, separate, somehow allow us to access underlying explanations of the data. One thing I realized in the last few years is that it's not enough to separate those variables, which ideally would be things like causal variables, but also to figure out the relationships between those variables. Maybe they're not independent. If you think about variables we manipulate with language, concepts like objects and verbs and stuff, they're not independent. We form sentences with them. And this notion of disentangling is also connected to the notion of modularization, right? In a way, finding good representations makes it possible to separate knowledge about the world into small pieces. And that's interesting because it connects to classical AI questions like rules and symbolic knowledge, and things we represent explicitly, usually with language, and that we can reuse in many ways. Okay. In this talk, I'm mostly going to focus on a special form of modularization of knowledge, which is knowledge about the joint distribution of random variables and how a joint distribution could be factored in many ways, and how it turns out that the causal graph, so a particular way to factor the joint distribution, makes the learner more robust to changes in distribution, and how we can use that to discover a causal graph. So that's also connected to, I think, something where much more theory is needed in machine learning. Most of machine learning theory is built on the idea that we consider one distribution, right? It's the distribution from which our data is coming. The data distribution, the training set, and the test set are supposed to come from the same distribution. But in the real world, as Léon Boutou was talking about just minutes ago, that's not how it is, right? We build a system based on a data set that was collected under some conditions in the lab or in a particular country, and then it's going to be used in a different place with somewhat different. Some things will have changed, right? As he said, he talked about stable aspects of the world, right? This is really important to think about. And so when we start thinking about not just a single distribution, but multiple distributions, we have to start thinking about what does it mean that the distribution changes, so non-stationarities, right? We can't just say it's a different distribution. They must have things in common. So Léon talked about invariant properties. And in this talk, we're going to look at particular invariant properties, which is causal structure, like A is a cause of B, even though the relationship between A and B may change a little bit, or there's an intervention which maybe decouples A and B, but other causal relationships remain the same. So there's a notion that some aspects of what we know about the world remain fairly stable under things like interventions by agents in the environment, and others change, maybe temporarily or not. And knowing how that knowledge can be broken into pieces in the way that there are lots of stable pieces is really important, because then we get the right tools to play the game of combinatorics, of being able to generalize in more powerful way than standard generalization. This is also called systematic generalization in linguistics and cognitive science. So for my part, the inspiration that really brought me to this work, there's of course lots and lots of inspirations, but the one that I want to recognize the most here is the thoughts coming from the book by Peters, Jensig, and Shopkoff on causality, and many years of interactions with Bernard Shopkoff, where they talk about this idea that there are independent mechanisms. Think about like physical mechanisms that explain the world. And that mostly those mechanisms are stable. They don't change even though we may intervene in the world. And even though most of those changes in distribution will be localized to one mechanism, if we don't have the right representations of data, it may look like many things change. So I think I have an example here, right? So here's a graphical model. Nodes represent random variables. And I don't know what the right space of variables is, but if I have the right space of variables, and I assume that the world is explained by these independent mechanisms, what it means is that when something changes in the distribution, it's going to be localized to just a small part of that graph. For example, I shut my eyes right now, and pixel-wise, the world is very different. But it's only one bit that changed, right? So the pixel space is a really bad space to think about causality. It's a really bad space to modularize knowledge. But a high-level representation where my eyes are closed as one bit in the representation is a really good representation. Okay, so that's what we're after. And we're going to use something really beautiful, a really beautiful property that arises and very simple. When we make this hypothesis that the changes in distribution are localized to a few parts of the world model in the right space, that because the change is localized, very few parameters need to be adapted. And because very few parameters need to be adapted, we need very little data to adapt to the change. So if the parts of the world that change can be captured by very few parameters tracking that change, then we have very small sample complexity to deal with that change. Or we can infer what the change is with very few examples. And I think this is a key to things like transfer learning, all kinds of agent learning, reinforcement learning, domain adaptation, the sort of robustness that Leon was talking about, and so on. So these are all like very general ideas, and now I'm going to tell you about specific implementation of this to try to do causal discovery. In other words, to figure out what is cause and what is effect in some set of variables. And the simplest scenario is we have two variables, and then later I'll tell you about how we can extend that to more variables. So with two variables, we can take the joint distribution and decompose it in a directed graphical model in two possible ways. Let's see, we have like these two ways, right? So P of A and B can be P of A times P of B given A, or P of B times P of A given B. So these are two possible hypotheses to represent the causal direction. In terms of the single distribution that we may observe in the training data, both are in general equivalent, that one factorization is not better than the other a priori. But if one agent changes, say, the cause, like let's say A is the right cause, and so that corresponds to a change in the marginal distribution P of A. And so if I have chosen the right model, which is P of A times P of B given A, and I have pre-trained it on the training distribution, then a new distribution I call the transfer distribution comes, and I continue adapting my parameters by maximum likelihood. What's going to happen is that the P of A changed, and so I'm going to have to change parameters. There will be gradient, but the P of B given A didn't change, and so the gradient on those parameters will be 0. And it's really trivial to prove that. And the fact that so few parameters need to change is going to be translated into a fast learning curve. So in that figure, what we see is on the x-axis, as we see examples of a modified distribution where the marginal P of A has been modified, we see the log likelihood on the y-axis getting better as the learner adapts to the change. And we have the two colors corresponding to two hypotheses, one which assumes a correct factorization corresponding to the direction of causality, and the incorrect one. And we see that with the correct causal hypotheses, the correct factorization of knowledge, the adaptation is very fast. But asymptotically, the two things meet each other, right? Because as I told you, if you have enough data, it doesn't matter how you factorize the knowledge, you can get both good training performance and good test performance. But it's in the early stages of adaptation, when there is not enough data, when generalization is difficult, that something interesting is happening. That's when the two models, the two ways of factorizing knowledge, the two ways of explaining causality are behaving the most differently. And that's where there's a signal. So if you wanted to do, say, model selection here to pick the right causal direction, then you should really pay attention to what happens very early on, after like 5 examples or 10 examples of the new distribution. If you wait too much, then there will be no signal. The band here is the uncertainty, right? So this is the standard deviation due to repeating the same experiments over different samples of the second distribution. All right. So that's if we have the right decomposition of knowledge, if we have the right causal structure. But if we don't, for example, if we don't even have the right variables that we're talking about because we're working in pixel space, then every parameter will tend to want to explain everything. And that's what we have typically in standard neural nets, the way we're using them today. They're not robust to those changes in distribution, because when there's a change, every parameter wants to help, right? Oh, I'm gonna explain this, and they all like move together, and so you need a lot of data to fix all the parameters in a coordinated way, right? You have to remember the parameters, they can't change independently of each other, and so you have to keep them coordinated, and that takes a lot of data so that to move all of them to now the right place, which is where the new world is. And that means they have forgotten the old stuff. That's catastrophic forgetting. If we now go back to the previous distribution, performance is really bad. Humans are not like that. We can recover from changes in distribution and go back to an old one, and very quickly. Like, you know, if you used to bike when you were young and then you don't do it for 20 years, try again for 10 minutes and it comes back, right? So this is, I think that we have to rethink how we structure our deep nets, and even ask questions about biology, but like how our brain's doing this, because we're doing this very clearly. And I think it's going to have impact on dealing not just with catastrophic forgetting and transfer learning, but something that people care a lot about in AI settings, like, you know, trying to get an agent to understand the world around it, where you have changes in distribution, you have new tasks that come in all the time, so-called continual learning. Right? So for all of these things, I think we would gain to better understand how to manage these changes in distribution and how to represent knowledge in our models to do that optimally. So what I'm proposing is, as a starting point in this research direction, to turn the hindrance that we normally don't like in machine learning, like non-stationarities and changes in distribution and not having enough training data for the new task and so on. Instead of seeing this as a problem, see this as a feature. It's not a bug, it's a feature. So Leon, I just copied a sentence from Leon's talk. Nature does not shuffle environments. We shouldn't. And as he said rightly, when we shuffle the data, we lose information. And that information tells us about how things can change in the world. And that's super important information, right? And what I'm proposing is to optimize how a learner adapts to those changes. If we shuffle the data, we can't measure that, we can't optimize it, we lost all of that stuff. So what I'm proposing is to turn that speed of adaptation as the world changes into an objective function, and more specifically a meta-objective, because what we want to know is how fast you adapt. So there's the normal adaptation, but we'd like to make sure that that adaptation is going to happen quickly. So it's like a second-order decision here that needs to be taken. At least that's one way to think about it. So, as a concrete thing, as a first step towards this very ambitious goal, let's consider a simple scenario where we just have two distributions, a training distribution and then a modified distribution. And we're going to do two things. We're going to optimize with respect to that speed of online adaptation. We're going to optimize an encoder that maps observations like pixels to a space of variables. And then in that space, we're going to have a graphical model, a directed graphical model in those experiments that captures the joint in that space. And we are going to try to figure out two things. We're going to try to figure out what is the right decomposition. In other words, which arrows in the graph should be present. What's the structure of the graph, which is a bunch of binary decisions. And we also, of course, want to figure out, given the structure of the graph, what are the parameters of all of the conditionals and marginals that are involved. But the thing that we're going to meta-optimize, the things that are stable according to our mental picture of the world, are the encoder that is defining what the variables are, and the structure of the graph. The conditionals, they can change because I'm assuming that as an agent comes and does things in the world, it might change a particular conditional corresponding to a particular variable that was modified due to an intervention. So again, the assumption that we're making and that we're trying to exploit is that changes in distribution are localized to just a few variables in the right variable space. So the more that is true, the more we're going to gain by optimizing this objective, which measures how fast the whole system learns and adapts to changes in distribution. Okay. So now we have to be a bit more concrete about what the meta-objective is going to be. So in our experiments, we define some graphical models corresponding to different causal structures. And for these graphical models, there will be parameters like the neural net, the parameters, the weights of neural nets that correspond to different conditionals. And those parameters theta will change after each mini batch, and we're going to have a sequence of these. And we'd like to see how many examples or how many mini batches we need to reach a certain level of performance. But a way to just measure that is the product of the likelihoods along the way. So we're going to have a likelihood for each possible structural hypothesis that says, okay, we want P of A given B times P of B, or P of B given A times P of A. So these are two likelihoods we get by making different structural hypotheses corresponding to different hypotheses about which is cause and which is effect. And then we're going to form a mixture to explain not just one example, but the whole batch of example corresponding to an episode where we have a new distribution. And to explain that whole episode, we're going to say, well, it either, all of that bunch of data either came from one model, the model that assumes that A is the cause of B, or the other one with some probability sigmoid of gamma. And gamma is going to be our parameter, our structural parameter or meta parameter, which we want to meta optimize, and that controls our belief as to whether the right answer is A is the cause of B or B is the cause of A. So the thing we're trying to learn here is just one bit in this really, really simple example. And to learn that, we have this single real value, which measures our belief into whether the bit is 1 or the bit is 0. Okay. And so we call this a kind of regret because it measures the accumulated loss under some belief that the right answer is either one structure or another structure through the mixture of these beliefs. And there are a number of things we can say about this objective, but maybe the most important is that if we do stochastic gradient descent on that objective, which remember is a meta objective, right? It's meant to optimize the meta parameters like the gamma here. If we do SGD on this and we converge with a properly decreasing learning rate, then the place where we land corresponds to the right answer in the sense that we'll have full probability on the correct hypothesis. And we can verify this experimentally. So on the x-axis here are the number of episodes. So each episode is, I've trained on some data and then somebody shows me a modified distribution. And after each of these episodes, I'm going to do a meta update of my hyperparameter or meta parameter gamma, which controls my belief about which is cause and which is effect. And we've done many different experiments with different kinds of parameterizations of the variables. Here, this is with just discrete valued variables. And so what we see is that the meta-learning converges to the right answer. Here it's 1 in this experiment, the probability that it gives to the correct causal direction. And the two curves here are interesting because they correspond to two settings where in one case, capital N equals 10 is the number of values of the discrete variables involved. So in one case, N is 10 and the other N is 100. So one case has more parameters and a more complex distribution to learn because there are more degrees of freedom. And that means usually generalization is worse, right? You have more things to learn, sample complexity is higher, you're going to need more data. But the cool thing is, it's in the situation where there are more parameters to learn that the meta-learning is converging the fastest, right? Because the advantage of the correct causal model or the correct modularization of knowledge in general is higher when generalization is more of a challenge because you have more parameters to tune for the same amount of data. Okay. So we tried this in many conditions. You can replace the tables in the model and the ground truth by MLPs. You still get this kind of convergence. You can, instead of having discrete variables, you can have continuous variables. And we started by looking at the case where the variables are just linear, Gaussian, related to each other, usual things. And again, you can recover the causal direction. You can look at the case where they're continuous, but they're non-linearly related, for example, through some splines. And the different colors here correspond to different distributions. So like maybe we train under the blue distribution, and then we have the transfer distribution might be the red or the green, something like that. And again, by seeing those changes in distribution, each time different, we gather information about the structural knowledge of whether A is a cause or B is a cause. Here, A is a cause. And then we run experiments where, in addition to learning the causal direction, we also learn how to transform some raw data into the right causal variables. And for this, we've run the simplest possible experiment where we only have two variables, and we consider just a linear transformation. So we assume A, B is the ground truth random variables, but they have been rotated, they have been transformed and mixed with each other, and we observe the result, UV. So that's what the learner sees. It doesn't see AB. And so what the learner needs to do is two things. It needs to learn another linear transformation that undoes the mixing, as well as figure out whether the transform variables here, U and V, are causally related, and which is cause and which is effect. And that works too. So we just have more meta-parameters to optimize, and we can track both the encoder parameters and the causal structure parameters, and see that as we show more and more distributions, changes in distributions, the thing collects enough signal to learn the right thing. Okay, so that was fairly toy experiments, but you have to keep in mind that in the causality world, even working with two variables is not easy. A lot of publications are about just that. And so if we want to look at the case with more variables, now we have to face combinatorially difficult problem, because whereas in the case with two variables, we may have two or three hypotheses. A is the cause of B, B is the cause of A, or none is the cause of the other. In the case of n variables, there is going to be like 2 to the n squared kind of potential answers to the question, what's the right graph, the right directed graph? So the way we are handling this for now is very, very trivial. We're saying we're going to parameterize our beliefs about what is the right causal graph by saying that joint probability distribution over all the graphs is just a product over edges. And for each edge, we're going to have, for each directed edge, we're going to have a bit that says it's present or it's not present. Okay, so there are n squared directed edges, and so on. So we have n squared bits to choose. And now there are issues like, well, are we allowing cycles? In theory, you can have cycles with causality, although in practice, you probably don't want to. And so we worked on various ways to handle that. What we converged to is a regularizer that that penalizes for cycles. Although you could do it differently. So for the conditionals, we're going to use MLPs in the usual way, encoding the variables either with one hots if they're discrete or just real values. And then we have this really nice theorem that tells us that if we decompose our beliefs in the way that I suggested, and just purely factor like a mean field approximation, the regret, which involves an expectation over that exponentially large number of graphs of the likelihood you would obtain for each graph, that regret decomposes fairly nicely into pieces that are independent for each conditional, for each variable. We still are going to have to sample now, right? We can't just add the two hypotheses because we're going to have an exponentially large number of hypotheses. So we're going to sample at for each episode, we're going to hypothesize a graph by sampling from our distribution, our belief distribution, and then measuring the likelihood. And that's going to give us a gradient, a stochastic gradient, kind of related to the reinforce estimator of gradient, if you want, but that's going to tell us how to change the meta-parameters. That's in the discrete case for like the edges. For the encoder, if the variables are continuous, then we can just backprop that objective function, or the one we get with sampling a particular graph structure. So that becomes like what we do in meta learning in many cases by backpropagating through updates. Right. So we do the usual things, very standard MLPs, but we're going to have different MLPs for each variable. And so for each of those variables, we're going to have potentially all of the other variables as input. But now that belief that a particular causal graph is correct is going to translate into a belief about masks that we're going to put at the input of these MLPs to say that only some of the variables are allowed, right? So if A is not allowed to be a direct cause of B in the graph, then we're going to just zero out that input to predict B given A, and B is only going to be predicted based on the other variables. So we've done this with 3, 4, 5, 6, up to 8, I think, nodes in the graph. And 3 is particularly interesting because a lot of the standard questions that people ask in causality really only come up when you start looking at 3 variables. So 2 variables is like not a very good case. I mean, not a very representative case of the complexity of learning causality. But 3 is, right? It's 3 because in 3 you have things like confounder variables, where one of the variables is a cause of 2 others, or colliders, where you have one variable which is caused by 2 others, and so on. And what we learned by doing these experiments is that it works a whole lot better if, in addition to what we were doing before, we also try to do inference on what the intervention was. So if you think about the way that humans deal with causality, when we observe a change in distribution, of course, we don't have somebody wiring in our head, this was the change that happened in the high-level space. But our brain tries to figure it out. This is called inference, right? So if the learner tries to guess what the change was, like which variable was involved. And by the way, that's pretty easy because the variable that got changed is going to have very bad likelihood under the current model. So if we use that information and we change our objective function appropriately with that information, then we get much more stable learning and we are able to recover those graphs fairly well. So I want to put this in a slightly bigger picture now for the time that's left. So I've talked about a research direction in which we want to learn high-level representations of the world where the variables are going to be causal variables, the kinds of variables that we name with language, potentially without having a language interface that tells that information to the learner, although it's going to be much easier to learn language if the learner has the sort of objective function and training framework that tends to make it learn the kinds of things we use language for. And I've talked about an assumption on how the distribution changes in that space of variables, that the change is sparse. But it's not just the change that is sparse, it's also the joint distribution itself, right? So in the right space of variables, kind of space, again, corresponding to words we use in natural language, the representation of knowledge in that space tends to be very sparse. And we can see this by referring back to the now almost forgotten work of classical symbolic AI, where people tried to codify knowledge about the world. And there are, many things I could say why it didn't work, but there are also some good ideas there. And the knowledge about the world in classical symbolic AI is just an enumeration of rules. You can think of each rule as a little nugget of knowledge that's fairly independent from other nuggets, and that involves very few variables. And a better way to represent that sort of knowledge compared to what we did, which was like just this directed graphical model, is a factor graph, and specifically a sparse factor graph. So a factor graph is a kind of graphical model where the joint is written as a product of many factors, so many potential functions. Each potential function involves a number of variables. So think of each of these as a constraint, like a statement that is generally true. And if it's not, then we pay a large price in probability. What's nice about this is that the same random variable which happens in our conditional on the right-hand side can happen in many rules. Like I can have many rules about a particular concept, and if I can modularize that knowledge into separate rules, I'll be again more robust to changes if one of them changes, right? So it goes back to this notion of modularizing knowledge, I think, that we need to think about. So I wrote a paper about this idea of representing knowledge in this sparse way in the right space in a paper in 2017 called The Consciousness Prior. And it's related to consciousness because the things that come to our consciousness, the things that we are aware of at any time, it's just a few variables, right? It's just like a sentence. It's a very small piece of information. It's a very small nugget that refers to very few aspects of the world. And furthermore, when we do reasoning, we manipulate these things, for example, to make a prediction about what will happen sometime in the future. And we only need to chain a few of these rules, a few of these nuggets of information, in order to make very powerful predictions about the future. Okay. So let me now make some more connections. In this work, we've considered a meta-learning setup, which I think is really interesting, and there's a lot of hard work, very important work about generalization and transfer learning with meta-learning ideas in the last couple of years. But maybe there's an even more general way of thinking about this, which, and the inspiration for this came to me by talking to neuroscientists. In the brain, it looks like there are different parts of the brain that are learning with different learning rates. So your early sensory areas can learn only very slowly, at least when you're an adult. And so if I give you glasses that are going to turn everything upside down, it's going to take you months and months to adapt to that. And it's the only way to do this properly is to have the early layers of your visual cortex adapt. If I show you a new object, this is happening much, more downstream, higher up in the hierarchy, the visual hierarchy. You can adapt very quickly. You just need one example, and that's it. And there are intermediate areas like this corresponding to different speed of learning. And again, I want to connect back to what Léon Bottou just talked about when he talked about things that are stable in the world. So it's not a black and white thing. At one extreme, yes, we have things that are very stable and stationary and invariant and all that. It's the same thing. And we want to learn these things in a way that is going to be robust to the changes that happen along the way, changes in distribution. So that's why we want to separate the stable stuff from the unstable stuff. But there may be different, degrees of stability, right? It's not all black and white. In fact, at the other extreme of things that can change quickly, you might not even want to do learning at all. You want to do inference. So what is inference? Inference is like super fast learning, right? It's like I see one example and I have found an explanation for it. I don't need to learn new parameters. I've instead modified some state variable that explains what they are. You can think of as a form of learning too if you consider the state variable as free parameters that are allowed to change really, really quick, right? So we have these different speeds of learning. And this work also made me think about, am I going over time here? Or, okay with time? All right. Nobody complains, so I continue. So there's a question that had bothered me for a long time, which when I started thinking about causality, like when you start about, one of the motivations for causality is that it helps a learner figure out how the world works, which is something we don't do well right now in machine learning. But what about infants? Like they don't move much, and yet they are able in the first 8 months of life or something to learn a whole lot of useful stuff about the world. And the work that I'm talking about suggests that even if you're not actively changing things in the world in a strong way, like infants can't do that, you can still learn about causality by taking advantage of the non-stationarities, by taking advantage of the hypothesis that there are agents out there that are changing things, like your parents. And by somehow modeling that, you can get at causal structure, just like the learner in my experiments. The learner in my experiments was not directing the experiments. The experiments were happening randomly. The changes in the screen were happening randomly, but in a way that was localized in the right space, right? So this may be interesting from the point of view of cognitive science as well, to understand how a learner that's fairly passive is still able to acquire information. But as we saw in our own experiments, if you know what the intervention is, because you are the agent that does the intervention, that information is very useful and allows you to learn faster about the causal structure. Even better, if you can choose where to experiment, this is what you want to do when you're exploring, then you can just ask the right questions. This is what science is about. And this is what children do as well when they play, right? They get bored if they don't get any information out of it. Okay, so I'm going to stop here. There are many things that I think could be done to follow up on this work, but I'd rather spend time showing you pictures and names of people that are working with me on these questions, including Tristan Deleu, Nassim Rahman, Rosemary Kay, Alexa Belanyuk, Anirudh Goyal, Sébastien Lachapelle, Chris Paul, Rémi Lepriol, and Simon Lacoste-Julien. Thank you.
We have time for a few questions.
Oh, thank you. Very interesting. So I wasn't quite clear what the encoder does. So it's taking in raw input, maybe pixels, and generating a set of finite number of random variables, which are nodes in your graph.
Yes.
So can you talk about like how you decide how many nodes? Because that is
there are lots of questions. So we only studied a trivial case where the encoder is deterministic. You'd like in general to have a stochastic one, or that can handle uncertainty because we don't observe everything. So we only handle the easiest possible scenario. And also we parameterize the encoder so that we didn't have to worry about collapse, right? So that we don't want it to lose information. So there are little details that one has to worry about in real life that we didn't have to care about.
But the likelihood is a joint configuration of these latent nodes.
Yes.
So how does that relate to the raw data? Because if you have a very lofty
So there may be many solutions that are correct, right? For example, you can have permutations, change in signs, and so on. And because those problems are so simple, we can recognize that this is a good solution, and we just score 1 when it discovers a good solution. One of the good solutions.
So I'm wondering if you thought about time series data.
I don't think we hear you for some reason.
Oh.
So he was asking if I worried about time series data.
Well, we learn in the time series sense because we live in the world, right? So all our data streams, if you will, have to be self-consistent, right, from moment to moment, right?
Well, no, that's the thing, right?
Well,
I'm proposing to exploit the changes in distribution that happen due to non-stationarity. So often the way people handle time series data is they stationarize it. And we want to do exactly the opposite. We want to exploit those changes as clues about what is stable and what is not stable in the underlying explanation for the data.
No, I understand that, right?
Okay.
But wouldn't it be, in a certain sense, easier, if we just started working with time series data, where the nodes in your graphs kind of become self-apparent because of the structure across time, right? And then the static images or static data that we tend to work with in machine learning become just a special case as opposed to the primary case.
Right, but I think the primary case should be temporal data because it's so rich in terms of changes in distribution, and we tend to not pay enough attention to it. Yeah.
Okay.
Thanks.
Hi. So as you were speaking about things being stable as you change from distributions, I was thinking about compression.
So maybe a better word than stable is that if you were to consider accumulating asymptotically, you would converge, right? So even things like learning new concepts is stable in a way because if you imagine learning more and more new words, it would converge. But things that are unstable would be, like random changes that are not going to be persistent in any possible way.
Yes, like noise, right? Or something like that. So I was thinking about compression, and when you started speaking about like going from the continuous domain to the discrete, isn't that kind of a compression bottleneck for this type of network? And so wouldn't that kind of be a factor as to why, or does that not make sense?
Yeah, I'm not sure I understand your question. So I think the ideas I talked about can work both for real and discrete variables. The connection I see to compression is, of course, the things that are stable have a lot of power in terms of compression ratio. So you should really try to find them to get good compression. Yeah, sorry if I didn't answer.
Okay. No, it's okay. Maybe it didn't make sense.
Maybe one more question.
Yeah, you mentioned that the sparse factor graph may be the best graphical model for the purpose. Yeah. But since it's undirected.
Well, best, I don't know, but better than what we usually do. Because there's always something better. That's what we do, right?
Okay, but it's undirected, so you may lose causality, which is a purpose.
Yeah, so I think we can just take factor graphs and add one bit of information per argument of the factor that says, is this like a causal, is this acting like a cause for the factor, or is acting like an effect of the factor? That's all. So that would be like a new kind of graphical model that doesn't exist, but it's a trivial mix of standard directed causal graphs and factor graphs.
Okay, let's thank Yoshua again.